So let me share the slide and that I will go accordingly. I cannot find, okay. Let me set. I cannot find my window to share you. What happened to it? Okay, now I have it. Can you see this slide?
Yes, sir. Signal classifications.
Yeah, sorry?
Yes, sir. We can see that.
Okay, no problem. So you see that at the beginning what we have done, because this was a preliminary first lecture where we have given an overview of signals and systems. Then we started classifying our signal. Okay, broadly we can categorize our signal into two broad categories. One is your continuous time, where your signal exists in all instance of the time over the duration of your signal. And we have our discrete time signal. Your discrete time signal exists on the discrete intervals. Those intervals are actually determined by the acquiring process of our signal. Okay, signal acquiring means your signal can itself be monitored in discrete interval of time, or you may have a continuous time signal that can be sampled to make it discrete, isn't it? So after having your signal discretized, we can process the signal further to make it digital for further processing that we have discussed in the last class. And at that time, we also understood that all discrete time signals are not digital, isn't it? Yeah.
Yes, sir.
এই রেসপন্ড না করলে তো বুঝতে পারবো না তোমরা ঘুমাইতেছো না ক্লাস করতেছো।
Yes.
When I will say something, you have to be very careful about that.
Yes, sir.
Okay. Then apart from this broad classification, we have to have some other natures of the signal that we need to investigate. Accordingly, we have to classify those two categories. Both these categories that we are discussing from now ahead will be applicable for both your continuous time signal and your discrete time one. Okay.
Yes.
Now we start with even and odd signals. Okay. This is related to signal symmetry. Symmetry means with respect to the independent variable, how your signal is oriented. That orientation of the signal with respect to the independent variable we call the signal symmetry. The oddness and evenness of a signal belongs to that signal symmetry. Probably in your earlier lectures or classes or even levels, you have heard about these two terms, even and odd signal. Have you heard about it?
Yes, sir. Yes, sir.
Okay. So this is not a new thing, but we will revisit the thing in the perspective of signal processing further. So if your signal is an XT, your XT signal is called even when this symmetry is applicable there. Oh, sorry. Your symmetry condition. Okay, just let me discuss a bit general. I will share whiteboard because some writing is needed in order to understand the basic phenomena regarding oddness and evenness of your signal. And if we annotate it on your PowerPoint slide, I need to erase it, otherwise it will cause a problem for the next slide. So let me use whiteboard, and you can also keep notes.
Yes, sir.
Okay, that's is it now visible to you?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
Fine. Then in accordance to our definition, that we are defining an event signal as xt is equal to x minus t. Then you need to know what is x minus t. X minus t means what? For example, if we want to draw a figure, then this is your time x. This is for continuous time signal time, and say this is your signal xt. This region is actually minus time, and this region is for plus time, isn't it?
Yes, sir.
So whenever we have a signal,
Yes, sir.
that we are putting a negative sign in time in the independent variable, what does it mean then? It means that we are flipping the signal with respect to this vertical axis. Okay, that means a signal appearing in the positive region will be reflected in the negative region. Okay, just for your understanding. Okay, consider that we have a signal something like this. It is a pulse signal extending from minus t to t with an amplitude equal to a. Now tell me, if we flip the signal or with respect to the vertical axis, will there be any change in this signal?
Yes, sir. No, sir.
Yes or no?
No, sir.
Because your t will go to minus t, your minus t will go to
E.
t. As a result, the nature of your signal will remaining same, isn't it?
Yes, sir.
Yes, sir.
And is it not that condition satisfying?
Yes, sir. For
Yes,
even.
sir. Yes, sir. For even, sir.
So this is your even signal. Even you can test it by using some other technique. Okay, that means you take a time in the positive region. Say this is your time t1 in the positive region. You will have a value of the signal. Okay, and you just go into negative time minus t1 and check the value of your signal. If these two signal values are same, that will satisfy this condition, isn't it?
Yes, sir. Yes, sir.
And is not this signal satisfying this condition?
Yes, sir.
So this is an even signal, isn't it?
Yes, sir.
Okay. Now let us consider another piece of signal, okay? That we have this signal, say something like this. Say this is your signal xt, this is your time t, this is 0t, this is minus t. Okay. Is this the condition that we have written earlier is valid there for this signal?
No, sir. No, sir.
Because if we flip the signal, you will see that your flipped version of the signal will be looking like this. If we flip the signal, your signal will be looking like this, isn't it?
Yes, sir.
Yes, sir.
This is t, this is minus t, okay?
Yes.
That means these two signals are not actually same. This can be made same only when if we can multiply this signal by minus 1, isn't it?
Yes, sir.
These two can be made same if we multiply this signal, say this flip version of the signal minus t by minus 1. So that signifies that these two signal will be equal when we multiply, for example, this signal x minus t with minus 1.
Yes, sir.
That is equivalently equal to minus x minus t. Is it not?
Yes, sir. Yes, sir.
Yes, sir.
So this is your odd condition of your signal, okay?
Yes, sir.
And this is your even condition of your signal. Are not those things very interesting and simple?
Yes, sir.
Okay. Now, apart from these two categorization of signal into even and odd, we may have our signal that will not satisfy these two conditions. Consider this signal. Just we are dealing with very simple configuration just for our easy understanding, okay? Say consider this signal xt now. Is that signal satisfying the above two conditions?
No, sir. No, sir.
Because this signal is not symmetric with respect to your vertical axis. Even there is no any, if we flip the signal, then what will happen? It will go in the opposite side, isn't it? It will go in the opposite side in this way, amplitude will be remaining same, time is this, isn't it?
Yes, sir.
Yes,
And
sir.
this become your x minus t. You see that your xt cannot be made equal to x minus t. Can you make it? No.
Sir.
As your signal is appearing in this way, you cannot make these two signals equal. This type of signal is neither odd nor
Even.
even. So you may have used signal, those signals are neither odd and nor even. All these things are discussed in your slide. I will not be showing it to you. Slide is shared with you. Okay, you can take a look later with your slide. Okay, please concentrate in this writing. If it is, if you can keep note, then it will be helpful for you. Okay. Now let us consider the signal that is not neither even and nor odd. So we are telling that we have this signal. That signal, not telling actually this is the fact that this signal, okay, is neither odd nor even. Actually, you see, your signal can be given either in the figurative form or it can be given in the mathematical form. Okay, in the mathematical form, how that signal can be written? Xt would be equal to A for 0 to T to T, isn't it? Is it not the mathematical representation of this pulse?
Yes, sir.
Yes, sir.
So either your signal can be given in the figure form or it can be given in the mathematical form. You can commute between these two forms, okay?
Yes, sir.
But figurative representation is more understandable than mathematical representation. That's why we say that a line word, thousands word, okay?
Yes, sir.
Very good. Now, how to handle this thing? Actually, that signal xt in general can be decomposed into its even part as well as its odd part. Microphone কথা বলার পরে just please mute it, otherwise noise will be picked up, okay?
Okay, sir.
So this is your equation that, for example, if we apply this equation for this signal can be decomposed or split up into two parts. One is even part, another is odd part. Now we need to know the technique, how to extract these two parts from this signal that is neither odd and nor
Even.
even. Okay, fine. Then if we have this equation with us, then let us flip this signal. If we flip this signal with respect to the time of axis, this flipping operation sometimes called reflection operation also. Because if we take a mirror, if we place a mirror on the vertical axis, then the image of the signal that is on the mirror will appear in the negative time side. For this reason, it is called reflection operation. So that reflected version of your signal, just you replace your time t by minus t. Then in this equation, you have to replace that time minus t, and your odd signal will also be reflected by minus t. Now, according to the definition of your oddness and evenness of your signal, your even signal will remain same, but your odd signal will change its sign from plus to minus, isn't it?
Yes, sir.
Very good. So you have your equation 1, you have your equation 2. Can we solve these two equations to find xc and xo?
Yes, sir.
Then you will see that your xe, the even signal, will be equal to half of xt plus x minus t, and your odd signal will be equal to, okay, can you just see the handwriting easily?
Yes, sir.
Okay, because I am feeling very comfortable because we have been given a device. That device is sometimes cause problem, but in fact, when I will get accustomed to it, it is very, very good. Okay, I can write like in a bamboo paper. Okay. So this is your equations by which you can extract the even part and odd part. Is that clear?
Yes, sir.
Okay. Can you apply these two equations to extract the even and odd part of our signal xt that is there in the figure? The first step is what? You have to prepare x minus t, okay? Then you add these two things together, then you average these two figure, okay? Now let us draw the flip version, okay? I will be using different color. Okay, fine. So this is your axis. If we flip our signal xt, it will go in this, it will come here, isn't it?
Yes. Yes, sir.
Is it okay?
Yes, sir.
Now next step is what? You have to add them together, isn't it?
Yes, sir.
Now, I am telling you something mathematical, okay? This was the equation for our original signal. Let us write the equation for x minus t. Your x minus t would be equal to what? It will be equal to amplitude will be remaining same. Your time is now minus t to t. This is equivalently equal to minus t 0, t2 0, isn't it?
Yes, sir. Yes, sir.
Okay, fine. If, for example, we don't have this figure with us, we have this mathematical equation. Usually mathematicians do not like to draw figures, particularly pure mathematicians. They always used to prepare equations, yes. But we do not like it actually. So if we want to add these two equations together like mathematician, what will be the value? Xt equal to, if we for example want to add them mathematically, xt plus x minus t, what will be the value? Is it twice a?
Yes, sir.
No, sir. The range is.
No, sir.
Yes, this is the thing. It cannot be twice a.
Twice. Yes.
because These two signals are not appearing in the same time duration, isn't it?
Yes, sir.
There is no any overlap between them. If the overlap is there, only the overlap region has common time, isn't it?
Yes, sir.
But non-overlap region will not have common time. As a result, they cannot be added. Rather, you have to write the equation in this way, that it is equal to a from minus t to t to t, isn't it?
Yes, sir.
Okay, then let us prove it by using our figure. If we add these two figures together, how it will look like? Within the time 0 to minus t to 0, there is no anything there, okay? For this region, your sum will be equal to the red signal, okay? Kotako, is it okay?
Yes, sir.
Then your green signal will be there where no red signal is there, okay? So this is what your green part, 0 to t. Is it not your xt plus x minus t? Is it okay?
Yes, sir.
Yes, sir.
And that is what that equation, okay? Now, if you want to find the even part, what you need to do, you have to multiply this sum by half. But multiplying the signal by a factor means its amplitude will be either increasing or decreasing, isn't it?
Sir.
Yes, sir.
So if we multiply it by half, then your signal amplitude will be equal to what? A divided by 2. Okay. Now tell me, is it not your even signal? The evenness property is satisfied here, isn't it?
Yes, sir.
Yes, sir.
So you have your even part extracted, okay? Now if you want to extract the odd part, what do you need to do?
You need to subtract.
You have to subtract these two signals. Subtraction means we can multiply the red figure, this one, by -1, then add with our first figure, isn't it?
Yes, sir.
If we add, for example, this figure, red figure with -1, if we add the red figure with -1, then red figure will be turned into this one, okay? It will be equal to -a and -t, isn't it?
Yes, sir.
Is that clear?
Yes, sir.
Yes, sir.
Okay, so this signal is actually -1 multiplied by x minus t, isn't it?
Yes, sir.
Yes, sir.
Now we add this signal with your green one. So there is no any signal in the time limit -t to 0. So this figure will not be changing. Then only your green curve will come between time t equal to 0 to t. Okay. So this is your signal xt. This is t. Okay. Then that signal is actually xt minus x minus t. Okay?
Yes, sir.
Yes, sir.
The amplitude will be a. Then you have to multiply this thing by half. Isn't it?
Yes, sir.
That will cause your signal amplitude to be half.
A by 2.
And if you look at this signal, is it not satisfying the oddness?
Yes, sir.
part? So this is your odd part. Okay. So in this way, you can extract the odd and even part of your signal. If your signal can be given either mathematically or it can be given in figurative form. Okay. In either way, you can go. These equations are equally valid for discrete time signal. Okay. I will be showing this thing, then going to the slide. Okay, inshallah. Fine. Let us apply this thing for your discrete time signal. Okay, DT type signal. For your DT type signal, your signal will be appearing as a sequence of numbers for each of your sample points. Now, the foregoing equations that we have learned can be transferred equally into our discrete time signals. That is simple. Okay, this is your evenness property. This is your oddness property. Then for neither on a nor odd signal, you can take your even part as average of your xt, xn plus x minus n. Similarly, your odd part will be equal to. Look, one important thing is that in this in most of the books, when we represent our signal in dt, they use a square bracket rather than parentheses, okay, to save the argument. So you have to maintain this difference, okay? That's it. So in this way, you see that your operations are same, only here the thing will be discrete, okay?
Yes, sir.
Okay. Okay.
Yes, sir.
Now we start with the same thing. Consider that our pulse that we have written earlier is sampled with 4 samples, okay? Consider now we have our n. It is sampled at n equal to 0 with a value equal to a. It is sampled at n equal to 1 with a same value. It is sampled at n equal to 2 with the same value. Sampled at n equal to 3 with the same value. So 0, 1, 2, 3. How many samples we have?
4 samples.
We have 4 samples. Okay, so this is your xn. This signal can be.
Sir, can you not write in the top, sir?
Yes.
দেখা
Sir.
যাচ্ছে না, sir.
But this figure it is.
Yes, sir. It is visible, sir.
Okay. Yes, I am also saying this thing because sometimes your pen is an electromagnetic pen for this region. Okay, if we cannot place it a bit aligned with the margin, then it goes in the non-writable region. Okay.
Yes, sir.
Can you see the red one?
Yes, sir.
Yes, sir.
Fine. Now your signal, like your continuous time case, your signal can either be given in the figurative form or it can be stated in mathematics. Okay, if you want to state this thing in mathematics, then what will happen? Your xn would be equal to a for n is n between 0 to 3, isn't it?
Yes, sir.
And n cannot be a fractional number. Okay, it must be integer because it is the number of samples. So we have 4 samples there. So if you want to apply the same principle that we have applied, this signal is actually neither odd nor even, because if we flip the signal, there is no any part in the other side. But I will decompose this signal into 2 parts, even and odd, like our continuous example. Then we will define our oddness and evenness property there. Okay. The next step is what? You have to flip our signal, isn't it? If you want to flip our signal, what will happen then? Your n will go to minus n, isn't it?
Yes, sir.
So it will be minus 3, one sample, minus 2, another sample, minus 1, another sample,
And
0 will not change, okay?
yes, sir.
So this is your x minus n. Is this figure visible to you clearly?
Yes, sir.
Okay. So next step is what? You have to add them together, isn't it? If we add them together, what will happen? I will be drawing the figure actually a bit in a separate place for your understanding. This is now n, okay? You see that we started with minus 3, then minus 2, then minus 1, 0. This is your 1, this is your 2, this is your 3, isn't it?
Yes, sir.
So you see that where the red signals are appearing, there is no any green signal, okay? So it will be coming there in this way. Now we have our green signal where no red signals is there. Okay. And this figure is actually xn plus xn minus 1. Is this figure correct? Did I make?
So
Yeah?
there is a value at
Yes,
n equals to 0.
Yes, you see that n equal to 0, we have 2 samples coinciding, isn't it?
Yes, sir.
For this region, what will happen? You will have a sample there with a value. If these sample values are A, this value will be equal to twice A.
Twice. Yes, sir.
Oh,
Overlapping.
overlapping. Yes. Now, can you test the evenness? For example, if we go at n equal to 2, you will have a value A. If we go n equal to minus 2, you will have a value equal to A. So it is satisfying this symmetry condition, isn't it?
Yes.
Yeah?
yes, sir.
So is it not the even part? Not exactly even part, but twice of the even part, isn't it?
Yes, sir.
Yes, sir.
If we want to have the even part, we have to divide it by 2. If we divide it by 2, then your amplitude will be A by 2. This amplitude would be equal to A.
A.
Very good. So can you draw the odd part?
Yes, sir.
Yes, sir.
If we want to draw the odd part, you see that in odd part you have to flip your x minus n to the with respect to the horizontal axis to make it negative. So our n equal to minus 3, n equal to minus 2, n equal to minus 1, 0. This is 1, this is 2, this is 3, okay? That signal will be coming into the negative region, isn't it?
Yes, sir.
And our original signal will be remaining same. So if we add them together, can you find how they can be added? You will have one value there, you will have another value there, you will have another value there. Okay. Is this figure is okay?
No, sir.
No, sir.
No, why?
At x equal to n equal to 0, it will be 0 value.
0. Yes, sir. No amplitude, sir.
No amplitude, so 0 should be there. That you have to be very careful. Whenever we are dealing with discrete time signal, we have to use the stem, okay? The length of the stem is the magnitude of the signal, and the a small circle on the top of the stem should be there, okay?
Yes, sir.
So if we do not keep anything there, this is undefined. So a small circle should be there that signifies that the signal value is 0 at that position, okay? Now, can you test it with respect to this condition? You see that if you go there at n equal to 2, you have a value A. If you go there at n equal to -2, you have exactly negative value, isn't it?
Yes, sir.
So this is your odd signal, okay? But not exactly equal to odd, twice of the odd. So we divide it by 2, then that amplitude will be equal to A by 2. This amplitude would be equal to minus A by 2. So in this way, we can separate our odd and even part for a discrete time signal that is neither odd and nor even. Okay. Now, is that clear? Can we go to our next slide?
Yes, sir.
Okay, very simple thing, okay? Only the thing is that you have to engage. One student is chatting, sir, my room internet is disconnected for the 3rd day. Okay, I will tell this student that they have to use their mobile phone. But I cannot reply to him while I am taking my lecture. Because one important thing is the issue, okay? We are having a problem. That problem is likely to occur from your part, also from my part, okay? We both should have the alternative so that we can engage in our learning and teaching process effectively, okay? This is not a burden for anyone. Rather, it is our responsibility and need. You got my point?
Yes, sir.
So that understanding should be with you. And another issue that I need to again remind you that our university will be going to OBE-based learning and teaching process. In that process, you have no way to remain ideal, okay? The reason is that when your program will be getting accredited, the people will come you will investigate your performance, that whether you have achieved your course outcome, program outcome or not. They will interview you. If you cannot respond and satisfy them, your program will never be accredited, and eventually your degree will not be accepted after a few years. Then it becomes a very big trouble for you. After your graduation, accreditation will not be possible. So be careful about engaging yourself to the utmost of your ability, okay?
Yes, sir.
So this slide we discussed, that scenario we discussed. This is your example by using mathematical equation. I will ask you to do by yourself. This is an example. I prepared it by using MATLAB. I am telling you from my first year that if you cannot use your computer in your learning will never be complete, okay? And try to use MATLAB to draw these figures. It is very simple, and you can easily identify that the original signal was never. Okay, look that your cosine omega t is cosine t is what signal or even signal?
Even.
Even, sir.
Okay, but if you multiply our cosine t by using e to the power minus twice t, would it be an even signal or odd signal? If your time is from 0 to infinity, it will never be the even signal, okay? Rather, it will be neither on and nor even, okay?
Yes, sir.
It will be looking like this. This signal is neither odd nor even. Even, okay? Just at this point, please try to remember it. Cosine omega t, if your t is between minus infinity to infinity, only when this signal cosine omega t will be even. But if your time duration is from 0 to infinity, will it be even?
No, sir.
It will not be even, okay? It becomes an unidirectional signal, and it is not neither even and nor odd, okay? Very good. So this signal is actually neither even nor odd. Now, okay, sometimes we multiply this signal with another signal. We call it UT. Do you know what is UT?
Unit function.
Unit step function, okay? it is unit step function. It looks like this, okay? Its amplitude equal, time is amplitude equal to 1, and it extends from 0 to infinity, okay? When we multiply some signal with this signal, only this part of your signal will exist, okay? You understand my thing?
Yes, sir.
For example, if we define this signal in this way, this is actually a bit undefined because we did not say anything about time. But when we multiply this signal with ut, then the definition will be what? Self-explanatory type, because when we multiply a signal by ut, your signal will last from time t equal to 0 to infinity, isn't it?
Yes, sir.
Just very simple, okay? Consider that we have a signal something like this. If we multiply it with this signal, then what will happen? This part of the signal left to origin will be equal to 0. Region is what? Region is there is no any value in this region of ut. Then eventually only this part of your signal will exist. This amplitude is 1, the amplitude will never change. So your signal will be something like this, isn't it?
Yes, sir.
Yes, sir.
So whenever we multiply a signal with a unit step function, that will make your signal actually symmetry of your signal will change. So this is your signal. You flip your signal in the negative time, it will look like this. You add them together, then this will be this signal. Okay, if you subtract them, this will be this signal. This is your even part, twice of the even part. This is twice of your odd part. So few examples are there in your book. Some problems are also there as practice problem. Answers are given there. Try to practice it. Okay, we will never repeat this in your exam. This is for your practice only. Okay. But your understanding will be tested in your exam. Exam policy is coming, evaluation policy is finalized. When I will get the order, I will let you know it. But at this time, although I have some understanding, but I cannot share it to you officially unless it is accepted by the competent authority. Okay, now we have another symmetry condition of oddness and evenness for our another type of signal. We call it complex type valued signal. Okay, you have already known that in our electrical engineering we encounter signal that can be real valued, in other cases complex valued. Can you give me an example of a complex valued signal? Yeah. Yeah, aso na nai.
Phasor.
Aso, are you there?
Yes, sir.
Yes, sir.
I ask you a question, okay? Complex value signal. Say if we have if we have a signal, okay, say xt equal to e to the power j omega t. Have not you seen this type of signal earlier?
Yes, sir.
Yes, sir.
It is going probably in the other region, okay. So is it a real signal or a complex signal?
So complex.
Complex signal, sir.
So we need this signal also in many of our purposes. Now, how the symmetry condition of a complex signal is actually determined. So this is the basic definition of the complex symmetry of your signal. Okay. If you can you understand the case that if we have a complex signal, if we flip it in time, that will be equal to the conjugate of your signal. Okay.
Yes, sir.
Then if this condition is satisfied by a signal, complex signal, we call it the complex conjugate signal, okay? Or conjugate symmetric signal, not complex conjugate, conjugate symmetric. Now let us, because we know that the signal will have a real part and imaginary part, both will be time varying. We have to understand individually how the real and imaginary part will be judged in light of our symmetry condition. Okay, we can easily write this equation complex signal by splitting your real and imaginary part. AT is the real part, BT is the imaginary part. J is the complex identifier, you know it. Now, if we take the conjugate of your signal, you know conjugation will cause the sign of our imaginary part from positive to negative or negative to positive, isn't it?
Yes, sir.
Okay, now let us examine the symmetry condition of 1.6 in this equation. This left-hand side is actually the flipped version of your original signal. Your right-hand side is actually the conjugate of your signal, okay? Now, if we start with this definition, and they should be equal, then what condition should be satisfied? Because this real part should be equal to that real part, and that imaginary part should be equal to this imaginary part, isn't it?
Yes, sir.
So now you can extract these two things out. This is what the equity condition for real part. This is what that condition for the imaginary part.
Yes, sir.
Okay, now can you tell me that what symmetry condition is existing for the real part?
Even.
Sir, even, sir.
Even. That means your real part is even and imaginary part will be
Odd.
odd. Very good. Okay, let us go to the next slide. Okay, fine. It is a simple example.
Of the real part and imaginary.
Yes, because you see in many of our problems, these two parts can be given, and sometimes you may be asked to determine whether the signal constituted by these two signal, the complex signal, is complex symmetric or not. Okay, that can be tested. For example, we are having a signal, say xt, that xt. Okay, that xt, for example, is constituted as by using the real part x1t and by using the imaginary part x2t. Okay, then we have to examine that whether your xt is conjugate symmetric or not. Okay, if this is your problem, then what you need to do, you have to test the real part first, whether it is even or not, and you have to test the imaginary whether it is even or whether it is odd or not, isn't it?
Yes, sir.
Okay. Now tell me, if this x1t and x2t are the real and imaginary part of a signal xt, is this signal xt is conjugate symmetric? Yes
sir.
or no?
Yes, sir.
The reason is?
X1 is even and X2 is odd.
Okay, very good. That's it. Okay, fine. Very good. Okay.
Yes, sir.
Okay, so in this way you can test the evenness and oddness of your signal. Very good, very good. But that's why I need response. Okay, if you respond, then I feel very happy to conduct this class. Okay, now we have another category, and this category is actually a broad category of I would say, and we have wide applications of this signal of electrical engineering. And you are having this term with you for the very beginning of your study as from the intermediate level, I think. Do you know about periodic signal? And
Yes, sir.
Yes, sir.
Okay. So periodic signal is actually, a period means or something is coming repeatedly after certain constant interval, isn't it?
Yes, sir. Yes,
For
sir.
example, say you are moving over the circumference of a circle in this direction. If we consider this point P, what will happen? If you make one revolution there, you will traverse a distance, say in time T. Again, if we make a second revolution, in the second revolution, you will also traversing the same time, same distance, but not in the same time, isn't it?
Sir, for every revolution, it will take same time for
Same time.
periodic signal.
Yes, sir.
It takes some time, but it will not appear at the same instant.
Yes, sir.
Yes, sir.
Say, for example, say you start with 0 time, 1t is there, one make evolution. In the next 2t, you will make
Yes, sir.
third revolution. In 30,
T.
like this, isn't it?
Yes, sir. Yes, sir.
The revolution, if your velocity is constant, only when this will happen. But if
Yes,
your
sir.
velocity is not constant, if you have angular acceleration, then that distance will not be same, although you are moving over the circle, isn't it?
Yes.
Yes, sir.
Okay,
Yes.
so that is the thing you have to consider. If you want to make an analogy between this movement and our periodic signal, precondition is what? Precondition is you have to say that our movement velocity should be angular, no, there should be no angular acceleration. Otherwise, this will take different time at different instant, okay? So actually that's why we call it sometimes when we define periodic signal, we start with this simple analogy, okay? That is equivalently equal to what? That if we have a signal, that signal is changing with time, but the part of a signal is repeating after a certain interval of time, okay? Like the cosine omega t, sine omega t, square wave, triangular wave, you have already known this thing from your basic level, okay? And from that t is called one time period, and from that time period we can define frequency. From that frequency we can define the angular frequency also. And you know this thing, don't you know this thing?
Yes, sir.
Sir.
Yes, sir.
Now I am very hungry, okay? I could not take my breakfast to that extent. So let me go to you the next slide. Okay, this is an example of a periodic signal and a periodic one. At this moment, I want to discuss few things with you because you see that those things are mathematical in general. Are not they mathematical?
Yes, sir.
There is nothing engineering there. Actually, all these things we are dealing with are mathematics. Now, if they are mathematical, then you have to apply all whatever mathematical topic you have learned in your earlier mathematics courses. Okay. You see that this is a square wave. What is the period of this signal?
0.2.
0.2 second. Okay. If it is 0.2 second, we can calculate its frequency, everything. So, and this cycle is being repeated, okay, isn't it? So
Yes, sir.
it is periodic signal. In the right figure B is actually a pulse. It is not repeating. It is your non-repeating type, non-periodic type signal. But another issue is that whenever somebody will ask you that, what is the frequency of this signal? A, what is the frequency?
Sir, 1 by 0.2
1 by 0.2 is equal to 5
hertz.
hertz, okay. Is this frequency, is this answer is actually correct? Well, just I am helping you to answer my question, okay? You learned your Fourier series earlier. With the help of Fourier mathematics, can you answer this question that if we say that this curve has a frequency, only one frequency, 5 hertz, is it correct?
No, sir.
No. Then the correct answer will be what?
The fundamental frequency.
Exactly. Very good. So this should be the fundamental frequency, okay?
Okay.
The reason is what? Why we are calling it fundamental? Actually, the reason is this signal only you sign because you know from your Fourier series. Okay, let me use your whiteboard because this concept is very, very important, okay?
Yes, sir.
In all of your understanding, this is very, very important. I in many of our cases, I did not find very what we call acceptable answer in most of the cases from my student. That's why I want to repeat it, okay, for you. You see that if we have a periodic signal xt, that signal can be approximated as something like this. That you learn from your Fourier series, n equal to 1. To that n is not sample number, it is a harmonic number, okay, to infinity, an, a constant, into cosine omega 0 nt plus bn into sine omega 0 nt. Have you seen this equation earlier?
Yes, sir.
In your Fourier series, okay. You see that in this equation, what are the unknown thing? Your unknown thing is A0, A1, A0, unknown thing is AN, and unknown thing is
Yeah.
Dn. Your omega 0 is actually equal to 2 pi divided by T, and that we call the fundamental angular frequency, okay?
Yes, sir.
Yes, sir.
And you see that actually, what does it mean? It means that a function xt that is periodic with period t can be approximated by a pool of functions of cosine omega t and sine omega t whose frequencies are the integer multiple of fundamental, isn't it?
Yes, sir.
And if we say n equal to 1, we call it fundamental. It coincides with our fundamental frequency, isn't it?
Yes, sir.
Or n is greater than 1, we call them what?
Harmonics.
Harmonics. Very good. That's what I want from you, okay? These are called harmonic frequencies. Actually, non-sinusoidal, for example, if we have a pure sinusoidal signal, either sine or cosine, we need not to analyze it because they belong to the Fourier category already. They will have a single frequency. But if we have multiple signals connected, they are not exactly equal to sinusoid, then what do you need to do? You have to analyze the signal or decompose the signal into its sinusoidal components. Okay, that is what your Fourier series actually do. Now the question is that not all sinusoidal component will be, sinusoidal function can be the component of a periodic signal. The reason is that your sine and cosine functions that is related to signal xt must be harmonically related. You got my point?
Yes, sir.
They must be harmonically related. If they are not harmonically related, then they will not be belong to, for example, this signal. For instance, consider that we have a signal where n equal to 1 exists, n equal to 3 exists, n equal to 5 exists. That means only odd values of n exist. So in some cases, some even values can exist, okay? In other cases, both your even and odd values can exist. But if we have a signal, for example, something like this, and if we are finding a signal that is falling between these two, are those signal will be the constituent of this signal?
Sir,
You
can you
understand?
repeat again?
For example, say this signal xt had only this scenario. Fundamental exists, only odd harmonics exist. But if an even harmonics will enter in this loop, will be related to xt?
No, sir.
No. So that is not harmonically related. Okay. In this way, whenever your sinusoidal functions will be given, you have to test whether they belong to that particular signal or not. They will only belong if its frequency become the integer multiple of the
Fundamental frequency.
fundamental frequency, and the harmonic number is also depend on the symmetry condition of your signal.
Yes, sir.
I hope you learned it in your Fourier mathematics. We will revisit it inshallah when time will come. So if this is what your case, then we cannot say that our signal that we have seen earlier, the square wave, will have a single frequency, okay? It will have frequencies. Those frequencies are the integer multiple of what? Fundamental frequencies of 5 hertz, okay? So in this way, we can have our even and odd signal learned. Now we have our another, okay, or not only this signal categorization valid for continuous time, it is also valid for discrete time, okay. In the case of discrete time signal, you see, our time is not there. We use sample number n, and that sample number n is actually an integer. Then the definition of your periodicity will be something like this. If after a finite numbers of sample n, if your signal will repeat itself, then we may call it a periodic DT signal, okay? And in this case, the frequency of the periodic DT signal is determined by using this equation, twice pi divided by n. The unit will be radian per sample. and this is what we will discuss much about it later, okay?
Yes, sir.
So at this point, you understand this in this way, but few things we need to clear that I will discuss here, okay? If we rearrange this equation, that n is equal to twice pi divided by omega. Whenever a signal will be given, its omega will be given. We have a wide varieties of signal periodic. So once your omega is given, then you can find your n in this way. But if you have a signal, say you are finding this ratio will not be equal to integer or even cannot be made integer. Will that signal be periodic?
No,
You
sir.
understand my question?
No, sir. Can you repeat again?
Okay. If we have our omega already with us, omega is the angular frequency of it may be fundamental, not fundamental, but a frequency of your periodic GT signal. This is given to you, or your signal is given from where you can find it. Now, in order to find the period of your signal n, you have to find this ratio twice pi divided by omega, isn't it?
Yes, sir.
Yes, sir.
Consider that when for a particular signal where omega is such that this ratio cannot be made integer, then will this signal be periodic?
No, sir.
No. The reason is that in the case of periodic, n must be
Integer.
integer.
Yes, sir.
Either integer or in general the ratio of two integer. Consider that we have something like this, n equal to 7 divided by 3, something like this. This is not integer but the ratio of integer. In this case, there exists a name of this nature. In terms of mathematics, we call this number that can be expressed by ratio of two integer. What is the name of that number? We call
Rational
it
number.
rational number. Very good. We call it a rational number. That means if your n become a rational number, then that rational number can be transferred into an integer by multiplying it with another integer m. What will be the minimum value of m that can make your n integer?
3.
3. For m equal to 3, we can make it integer. In this way, we can find the period of your signal, periodic DT signal, if this ratio can be expressed as a ratio of two integers. Then the minimum value of m that will make your signal periodic, we call it fundamental frequency of or fundamental period of your signal. Okay, we will talk much about it later. Okay,
Inshallah, sir.
and if this thing will not be satisfied, then your signal will not be periodic. Okay, in your book you have few rudimentary problems. Okay, you can solve them. To answer is given there for your practice. Okay. After finishing our preparatory lesson, we will also discuss about some problem, inshallah. So with this thing, let us proceed further. Okay, these are the example that we have discussed earlier. Your first figure is a periodic signal and your second figure is a periodic one. Okay. And another issue is signal can be your deterministic or your signal can be random. Okay, in your earlier course, didn't you attended a course RSP?
Yes, sir.
Random signal processing. Probably you know about this definition more better than me. So you try to understand from this from your learning. Okay, when we will encounter it in this course, probably we will not be dealing with it undeterministic or random type signal. Now this is what another perspective of signal processing. Although it belongs to circuit theory, but still some definition is needed. It is generally used in our signal processing. You would say customarily used. Okay. You see that in our case, our signal can be what? Either voltage or current, isn't it?
Yes, sir.
So we can, but these two quantities are not enough to characterize our signal. We have to find the power and energy of our signal also. So when we, if we consider, forget about your power factor or impedance or something like this. Okay, this is a very general course. For this reason, we are dealing with real quantities only. So up to now, we have this thing with us. Let us concentrate with real quantities only. Okay, if this is our equation, then depending on the value of R, your power will be determined. This power PT is actually continuously changing with time. We call it instantaneous power. In your first year, when I introduced you with alternating circuit, probably I have introduced you with instantaneous power, average power, RMS value of current, average value of current, isn't it?
Yes, sir.
Okay, that you know this thing. In this signal processing technique, it is actually very general technique. We assume that we have a 1 ohm resistance connected in our system. Then instantaneous power can be either the square of your voltage or the square of your current. So in general, it will be the square of your signal. That X can be voltage, it can be current. The energy of your signal is defined by using this equation. You know that if you have an instantaneous power, you have to sum up your total powers to get your energy, isn't it?
Yes, sir.
Because and a power can be calculated from energy by dividing it with time. It is that power is the average power, and average power of a system should remain constant. Now, with this two categorization, we have to know that how these two things will be evaluated if your signal is given, and accordingly we have to categorize our signal, that in which category the signal belongs. That categorization is made using this principle, okay? Can you see this? Okay, you see the first bullet where what is written there, an energy signal is a signal for which your energy should be between 0 to infinity. Okay, that means a finite energy should be there for your energy signal. And in that case, we will see that the average power of that signal will be equal to 0. Because if we have our time, as your signal will not exist forever, for this reason, your average power would be equal to 0. Now, if we have a signal where your power will be finite, this is actually average power, not instantaneous power. Then if your power is presenting always from 0 to infinity with that limit, then in that case your energy will be infinity. So your signal actually, okay, I will illustrate it with an example, then I hope it will be clear to you. Okay, just see this text, it is from your book. Oh, by the way, have you downloaded the book? Hey, আসো তোমরা এখানে?
Yes, sir. Yes, sir.
Yes, sir.
So this thing is very important for you. Can you see it?
Yes, sir.
Yes, sir.
The text is very important, okay? The energy and power classifications of signals are mutually exclusive. Mutually exclusive means what? They cannot be mixed together. In particular, an energy signal has has 0 time average power, whereas a power signal has infinite energy. Okay, that is very important to be understood, that a signal cannot be simultaneously a power signal and an energy signal. Okay, let me discuss a bit about it, then I will go to the next slide. Okay, or I can go to the next slide, then discuss about it. Okay, no problem. Okay, let us consider this signal. What is it? Is it not a, okay, we have already defined UT, didn't we?
Yes, sir.
It is a unit step function, isn't it?
Yes.
Yes, sir.
Okay, fine. It is a unit step function, it will look like this. Again, I'm rewriting it, okay? This is in UT, amplitude would be equal to 1.
Yes, sir.
This signifies that that signal is existing from where to where? From t,
Zero to infinite.
okay, from 0 to infinity. Okay, fine. Now consider that a equal to 0, alpha equal to 0. If your alpha equal to 0, then it becomes what? It becomes a what
One.
type of signal? This should be equal to 1, then it becomes a step with an amplitude equal to a, isn't it?
Yes, sir.
Yes, sir.
Then if we want to calculate the energy of that signal, that means integrate the square of this signal from 0 to infinity, what will be the value?
Infinite.
That means the energy will be equal to infinity. So this cannot be an energy signal. This is a then power signal because average power will be existing. Now you consider that signal is multiplied by this exponential with a value a alpha positive but not equal to 0. Then your signal will look like this, okay, depending on the magnitude of alpha. Either it will be decaying faster or it will be decaying slower, isn't it?
Yes, sir.
Okay, now tell me, now your signal, is it now energy, now is your energy is now equal to infinity?
No, sir.
Yes or no?
No, sir.
Would the energy be infinity now?
No, sir.
No, sir.
For a is greater than 1, a is greater than 0, but a is not equal to 0, it will never be, okay? Because this is not equal to infinity. A finite energy will be there because of this damping factor. So it is an energy signal. If we integrate this signal by using a simple integration, you will find that this is what the energy of your signal. You can easily verify it by setting the value of alpha. You see that if your alpha equal to 0, the value of E will be what?
Infinite.
Energy will be equal to infinity. So this is an example of your energy signal, as well as it can be a power signal if your A equal to
0.
how many minutes we have?
Sir, 2 minutes.
2 minutes. Okay, then I am giving you the percentage. Many other examples are already there in your book. Try to have a look on it. Okay.
Inshallah, sir.
Okay, when I am giving percentage like your earlier things, you have to respond and go to your visible mode. Okay.